We've looked at acids and bases before. We looked at them in grade 8, looked at them in grade 9, and in grade 10. So let's just remind ourselves of what we already know, that acids and bases affect indicators. So if you've got bromothiamyl blue, it will go blue in a basic environment and yellow in an acidic environment. If you've got universal indicator, it's going to go red if you're acidic, and it's going to go blue or purple if you are basic. Aqueous solutions of both acids and bases will conduct electricity. Why is that? That's because they've got ions present. We're going to look at that ionization in a little bit more detail, but let's just do one example. If I, for example, have HCl and I put it into water, I am going to get the H3O plus ion and the Cl minus ion. Those ions are in aqueous solution and are therefore free to move. Also, if I were to take something like sodium hydroxide and I put that into water, it's going to turn into Na plus ions and OH minus ions in aqueous solution, and therefore you're going to land up with ions again that are able to conduct electricity. Acids will neutralize bases, and bases will neutralize acids, and we'll discuss that in more detail in a second as to exactly why, but we all know that they are basically the opposites of each other. Acids have got a sour taste. If you put a metal into an acid, you'll get salt and hydrogen. Remember, the test for hydrogen is that it causes a flame to go pop. And then if you take carbon, if you put any carbonate into acid, you're going to get salt plus water plus carbon dioxide. So let's say I put some calcium carbonate into hydrochloric acid. My salt is going to be calcium chloride, which is CaCl2 because calcium has a valency of 2 and chlorine has a valency of 1, plus water plus carbon dioxide, and that is going to just need a balancing number like that. What do we know about bases? We know that they feel soapy in aqueous solutions. Just carbon dioxide causes clear lime water to turn milky. So, there are a whole lot of models on acids and bases and everything, but the one that we're going to study is called the Bronsted-Lowry Theory, and it defines, and you need to know these definitions, an acid as a proton donor and a base as a proton acceptor. So when an acid-base reaction takes place, the acid donates its proton to the base, and the base accepts that proton from the acid, and we call those a conjugate acid-base pair. So they are paired together. Proton transfer is called protolysis or a protolytic reaction, working with protons. Acids that donate more than one proton are called polyprotic. So for example, sulfuric acid, which is H2SO4, has got 2 protons, 2 hydrogens, so that's going to be diprotic. And phosphoric acid, which is H3PO4, is going to have 3 protons to donate, so it is called triprotic. Anything with more than 1 is called a polyprotic acid. So, this is what they're going to ask us mostly in an exam, and that is to pair up acid-base pairs. So let's look at how we do that. Hydrochloric acid and water. We can break that up into hydrogen and chlorine, hydrogen and oxygen. If the hydrogen goes onto the water, you then get H3O+. So this stuff over here donated a proton to the base. Then it became H3O+. It's got a reversible arrow. Let's go backwards. If this lost one of its hydrogens and donated it to the chloride, we would land up with hydrogen chloride. So in a reversible reaction, you've always got an acid and a base on the left-hand side of the arrow and an acid and a base on the right-hand side of the arrow. Let's look at the base. The base accepts the proton and becomes H3O+. The acid donates the proton and becomes chloride minus. So this acid turns into this base. Going backwards, this base accepts this proton and becomes this acid. This acid donates a proton and becomes this base. So this is an acid-base pair, and this is an acid-base pair. The hydrogen chloride donates a proton and becomes chloride. The water accepts that proton and becomes H3O+. In the reverse reaction, the H3O+ donates the proton and becomes water, and the chloride ion accepts the proton and becomes hydrogen chloride. A strong acid donates its protons very easily. A strong base accepts protons very easily. The stronger the acid, the weaker its conjugate base. That sort of makes sense if you want to, because if this donates very, very easily, this is not going to go the other way very easily. So the forward reaction proceeds with ease, strong acid. The reverse reaction proceeds badly, and therefore that is a weak base. So it's always going to be favoring either the forward reaction or favoring the reverse reaction. We call water an amphiprotic substance. Amphi is like an amphibian, can live in both water and on land. It's two things. Okay, so it can be two things if you want to think of that for amphiprotic. So it can either be a proton donor or it can be a proton acceptor. It can do either one. So water is an amphiprotic substance and it can behave as either an acid or as a base.